All right. So we left off last class talking about confidence intervals. So we were going to use our sample mean, right? We were then going to add and subtract to that a certain number of standard deviations away from that mean that would give us alpha over 2 on each side of the interval. Right? We then said we were going to multiply that by the standard deviation of us sample means, which we have the equation for that, which was just the square root of the variance we sampled from over our sample size. Okay? And actually, I'm going to want to do something here in a second, so I'm going to rewrite this just to be a little bit bigger here. Our population variance we sampled from, the data we sampled from over our sample size. Okay? So that's kind of where we left off. We hadn't worked through an example yet, but I wanted to start talking about things that change this confidence interval. Right? So if I think about the first thing I can change is setting things with different levels of confidence. Okay? So if I had, let's say 1.96, and that gives me an area of 0.025 to the left of it. If I want to say something with a higher level of confidence, right, going say from 95 to 99, right, let's say this is a 95% confidence level z-score. Higher levels of confidence correspond to smaller alpha values. Smaller alpha values, if I divide it by 2, that's going to be a smaller area in the tail. So to get, say, 0.005 in the tail, I'm going to have to use, and this, sorry, should have been negative 1.96, a larger negative value, right? Or an absolute value, a larger value. So as I go to higher levels of confidence, my alpha, the area I want in the tails, are going to get smaller, which means I'm going to have to use a higher z-score. So when we go to higher levels of confidence, or alpha, gets smaller, so as alpha goes down, kind of our confidence intervals, right, that would give us a higher z-score. We're adding a higher number to our sample mean above and below. We're going to get a wider confidence interval, or a greater, however you want to think about that, a larger confidence interval. Okay? So that's the first thing. So what happens to that confidence interval if instead our original data has a higher variance, right? Well, if this is higher, what's going to happen to this kind of margin of error? We said we can call this our margin of error. What's going to happen to this? Well, it's going to get larger as well. Adding and subtracting a larger value to the sample mean is going to make that confidence interval get wider, or larger, however you want to say this. And that's even if we kept the level of confidence the same, right? Even if the z-score doesn't change, if the original data has a higher variance, it's going to increase the size, or kind of the width of our confidence interval. So what's the final thing we can change? The final thing we can change is, what if we take higher sample sizes, right? If I take higher sample sizes, what's that going to do to the standard deviation of my sample means here? A larger denominator, so that fraction is going to get smaller. If I then add and subtract a smaller value to that sample mean, my confidence interval for higher sample sizes actually gets narrower, or smaller, right? So taking high sample sizes is great, because what ends up happening is I can keep a really high level of confidence, right? Even though my z-score might be a little bit higher, I can say things at a high level of confidence, but if I take really, really high sample sizes, it's going to decrease the size of this enough to where I can say things at a high level of confidence for a very narrow range of values, which is ultimately what we want to do. I want to be able to tell someone with 99% confidence the sample mean is between, 34.1 and 34.2, right? That would be awesome, right? So that's kind of, taking those higher sample sizes is going to allow us to do those kinds of things. Oops. So that's kind of where we're at, right? Let's work through a few examples with these confidence intervals, right? So we just talked about all these things up there on the board, but here's kind of a summary of them. So let's say we've got this production process. We're making hockey pucks for the, I don't know, NHL or something. And they come to us and say, well, we want to make sure that, the hockey pucks we're making weigh a certain amount so that meets regulations of our league. Maybe they want to know, is the true mean of these hockey pucks, I don't know, 9 grams, right? Well, even if the true population mean was 9, if we grabbed 49 hockey pucks off the assembly line and we see a sample mean of 7.5, well, that seems like it's fairly likely, right? I mean, it's not very far away from 9. And so we want to build a confidence, interval around this sample mean and figure out with 99% confidence what range of values based off the sample evidence I found could the true population mean be in between, right? What range of values would include the true population mean? So I have the sample size of 49. I find my sample mean of 7.5. If I have the 99% confidence interval, my alpha would be what here? Alpha is just the area outside the interval in decimal form. So, right, so if I have the 99% confidence interval, remember if we go back last class, I have it somewhere. Oh, I skipped it. There we go. Oh, it's somewhere. Here we go. Remember, to get alpha from the confidence level, alpha is just like the area outside the interval in decimal form. So for the 99% level, alpha is 0.01, right? Because the percent outside the interval is 1% in decimal form, 0.01. 90% confidence interval, percent outside the interval, 10% in decimal form, 0.1. Right? It's the easiest way to remember it. So for the 99% confidence interval, our alpha is 0.01. Okay? And then let's assume that we only sampled 49 pucks off this assembly line, but we know that the machinery, like the way it pours, whatever the material is into these molds, it has a variance of 49 grams. Like we know the population variance. Okay? So first thing we do is identify these 4 pieces of information. We're given these. We already talked about what alpha is. Divide alpha by 2 and find the z-score that would give you alpha over 2 kind of in the lower left tail. We could do the intermediate step, which is calculate your standard deviation, right? So that was just this formula. And then from there, just plug everything in that you have into this confidence interval equation. Now, instead of doing step 3, you could just put it all into one formula, right? Instead of finding this first and plugging it in, you could kind of plug all that into one formula and get the answer, right? Just whichever way is easier for you to do, right? Sometimes doing the intermediate step, I think helps. So for this example, we have our sample mean of 7.5, our sample size of 49, our population variance of 49, and our alpha is 0.01. Okay? So we look up alpha over 2, which would be 0.005, right? 0.01 divided by 2 is 0.005. So we go to the table. This is from another class. We'll go to the Z table. We're trying to find 0.005. Looks like the closest we can get is these 2 values, right? So negative 2.57 and negative 2.58. We'll take the absolute value, the highest, the one that's higher in absolute value. Absolute value just means drop those negative signs, so 2.58. Right? So we now have our z-score of 2.58. We calculate that standard deviation of our sample means by plugging in our population variance, plugging in our sample size, and then we plug this value, the z value, and the sample mean into our confidence interval equation, add to get the upper bound, subtract this margin of error to get the lower bound, and we get at the 99% level, we would have to say that with 99% confidence, the true population mean for this weight of the hockey puck is in between 4.9 and 10.1 about, right? Which seems like a pretty wide range, right? I mean, it includes the desired, whatever I think said it was that NHL wanted it to be 9. Well, it includes that value. That could be the true population mean. But the true population mean could also be 5.2, right? There's a pretty wide range of values. And so what's one way we could try to narrow this down a little bit? The one thing that we really have the greatest influence over, keeping the same level of confidence, I could take We just talked about the things that change this confidence interval. How could I narrow down this range of values? Not smaller, right? Because if we take a higher sample size, that decreased this, it meant we were adding and subtracting a smaller amount from that sample mean or narrowing our confidence interval, right? So we actually want to increase our sample size because it's the denominator. Yep. So we increase our sample size, we could narrow this range down a bit. So maybe go back to the assembly line, grab another 49 hockey pucks, and calculate our sample mean of what? We'd have 98 then, right? So increase our sample size a bit, okay? All right, we'll keep working through a few more examples here. So let's say we go back to that birth data, and we have this kind of infant gestation or length of the pregnancy, and the population variance is only 9 weeks, right? We take a sample of 81 births. Actually, before we go to this, well, I'll show you on this example instead. So we have 81 births. We find a sample mean from those 81 births of 38. What's the 95% confidence interval for the length of a pregnancy or gestation weeks? Well, the 95% confidence interval, our alpha would be what? 0.05. Right. So we have these possible answers. We really can't rule any of these out. I mean, one of the things we know has to be true is each confidence interval should be centered around our sample mean. Looks like all of these are. Right? So probably nothing I can rule out right away. Let's just go through the steps. Identify what we need. So we have our sample mean, our sample size, our population variance, all given to us. We said this, alpha is 0.05. I now need to look up my z-score. That gives me alpha over 2 on either side of the interval. So that ends up being 1.96, but we'll kind of double check that, right? So 0.05 was our alpha. Divide that by 2, 0.025. We hunt for 0.025, and it looks like right here. That's actually an exact number. That's kind of nice. Negative 1.96. We said we can ignore that negative sign, right? We're just using 1.96 because it's already built into our confidence interval equation, right? What we were really wanting to do, oh, I grabbed the wrong marker. So I'm gonna get rid of this too so I can draw this up a little bit higher. So what we were trying to do when we get that z-score is we want alpha over 2 on either side, right? So if I look up alpha over 2, because the table always looks at the area to the left, it's always going to give me that negative z-score, right? Well, that was the one. I'm going to go that many standard deviations below my sample mean to get the lower bound. So that's why right, we subtract this to get the lower bound, but then we add that positive value of z-score to the upper bound. So I can look up alpha over 2. It's just that I have to remember I can ignore that negative sign because it's already built into my confidence interval equation. Now, a different way I can think about this is if I just want to find the positive z value that I can just plug in there, what we would actually look up is, well, if I know that there's alpha over 2 to the right of this value, when I go to the table to find it, I would actually look up 1 minus alpha over 2, right? Because that would be the area to the left of that value. Now, you don't have to do that. You can just look up alpha over 2 and remember I don't need the negative sign for confidence intervals. But that's really another way of thinking about it as well. Just trying to give you different looks here. So anyways, we find that it was 1.96. Now that we have our z-score, we could find the intermediate calculation, which is the standard deviation of our sample means. Plug in our population variance and sample size. We have a third. Plug everything into this confidence interval equation. Remember, this guy right here, just another way of writing that standard deviation of my sample means, right? So I don't have to do the intermediate step. Instead of doing step 3, I could have just plugged all my values into here. I'd end up getting the exact same answer, right? It's just adding another step to kind of double check I'm not, I don't know, having more things going on in that formula where I need more parentheses and, you know, it's a little bit easier to do in our calculator if we do it this way, okay? Now, just looking at this, what do you think is probably going to be true about the range of values? Well, before, what? When we look at the hockey puck example, we had a variance of 49 and a sample size of 49, okay? In this example, our variance is only 9, right? And our sample size is 81. So what we did there was, well, we increased n, so that's going to make this smaller. We decrease the population variance, which would decrease the standard deviation, so that should make it smaller as well. And we went from the 99 to 95% level, so that actually is going to, actually make sure we went from the 99 to the 95% level, which means that our alpha is going to be larger, which means to get that area in the tail, we actually need a smaller z-value. So everything here is going to be smaller than the previous equation, right? So we look here. 2.58 is now 1.96, and our standard deviation of our sample means, instead of being 1, is now 1/3, right? So because we took a higher sample size, because the original variance of the data was smaller, and because we are choosing a lower level of confidence, we could actually get a pretty tight range of values. In fact, it's almost like a range of 1, right? Before we had a range of 5, now it's just a range of 1.
So, looking at that equation, where does the alpha level come in? Is that the z-score?
Yeah, the z-score, right? So if we think about here, let's say this z-score before was negative 2.58, and that gave us an area of 0.005 here, right?
Okay.
If I now want the area was 0.025, so I know to get a larger area, I'm going to have to start moving out this way. That's going to give me a z-score closer and closer to 0. So as that z-score gets smaller, I'm adding and subtracting a smaller amount to my sample mean for my confidence interval. Does that make sense? Kind of. That's probably the trickiest one, because it's like there's 3 things, right? It's like, okay, if I want a high level of confidence, that's actually going to make alpha smaller. And if alpha gets smaller, that's actually going to be a value that's further from 0 or larger in absolute value. So it is kind of like going back and forth with what you're actually saying. But if you kind of have it drawn out, I think the visual kind of helps keep that clear. Okay. Any other questions on that one before we keep moving? We'll work through one more example, and then we'll do a little bit in Excel. So this example might seem stupid, but I think hopefully by the time we get to the end of it, it'll make a little more sense, right? So let's say I go over to the rec center, I grab 35, 40-pound weight plates, right? They don't all weigh 45 pounds. I weigh them all and find a sample mean of actually 46.5. So I have a sample mean, I have a sample size. Let's say, I don't know, I look up the company, and they claim based off their machinery that their population variance is 25, right? Because they use multiple types of metal, it doesn't all get mixed up the same. Every pour into the mold is a little bit different. So we have our population variance, our sample size, our sample mean. Now let's assume I say, what's the confidence interval that corresponds to an alpha of 0.1? So here I'm being given alpha, but I can work the other way. So what level of confidence would an alpha of 0.1 be? 90%, right? Because alpha is the area outside my interval, 0.1. So the probability of being within the interval would be 0.9. Percentage form, 0.9 is 90%. Okay, so I can work in either direction here. Now, which of these confidence intervals could I actually rule out right away? There's one in particular. It's actually 2 I can rule out. What has to be true about the value of 46.5 relative to my upper and lower bound? Should be smack dab in the middle, right? Well, first of all, let's look at D. Why can't D be my confidence interval? It doesn't even include the sample mean, right? I'm supposed to be centering this confidence interval around the sample mean, and D doesn't even include it. So it can't be an answer. If I look at, which one? I look at B here, notice 46.5 is about 2 away from 44.55, but it's about 3 away from 49. So B doesn't work because the sample mean is not exactly in the middle of that confidence interval. Right? The other two, I think if we check them out, 46.5 is exactly in the middle. So we have to actually do the work. Right? So we identify what, the information we were given. We had alpha here, so it was kind of an easy one. What will the z-score be for alpha over 2? Well, if my alpha is 0.1, if I divide that by 2, that's 0.05. So I go to my table, find okay, so in between these two values, so 1.64 and 1.65, take the higher and absolute value of the two since they look negative, 1.65. Once I have that, right, I just calculate that intermediate value, which is the standard deviation of my sample means. I had that population variance of 25, sample size of 35. Now it's just a matter of plugging everything into that confidence interval equation, right? Here's my z-score. Here's that standard deviation of my sample mean that I calculated. Here's my sample mean. If I do that, I get a confidence interval at the 90% level, that the true population mean for these 45-pound weight plates is somewhere between 45.1 and 47.9. So why is this an issue? Well, if the product is supposed to weigh 45 pounds, I can tell you with 90% certainty the true mean is not 45 pounds, right? And this might not seem like it matters when we're just talking about weights in a gym, but if this is like steel beams holding up, used to make buildings, or we're talking about drugs that are supposed to have a certain CC in them, it's pretty, we can use our samples to make sure that the production process is doing what we think it is, right? Giving us the desired kind of population mean for our product, even though we can't observe every single unit that's produced, right? We can grab some off the assembly line, but we're not going to sit and test every single one. It's probably not a feasible option in a lot of cases, okay? Any questions on this before we keep moving? Okay with this? All right, so let's do a little bit of work in Excel, okay? So on Canvas, let's see if I can get this, there we go. There is a confidence intervals example file, right? So if we go, let's pull up, there we go. So we go to Canvas, we go to Files, we go to in-class data. There's this confidence intervals example, right? So if we open that up, okay, I'm going to delete kind of this, well, this and this. I'm then going to delete these, and we're going to kind of create this. Don't worry about this. This was some stuff I was doing not for this specific example. It'll be something we'll talk about later. So let's say I'm looking at total undergraduate enrollment, and I have a sample of Division I schools. So I can just find the mean, the sample mean, by using that average function. Find the sample mean for their total undergraduates, right? So Control Shift or Command Shift on the Mac down arrow, hit Enter. I've got this nice sample mean. Now, I think the original value I had in this file was a little bit different, but let's just assume that someone tells you that the population variance is 68 million, right? So 68 and what, 6 zeros there. Let's just start off all with that. Let's assume someone gives you that population variance. We can't observe the population data, so that's going to be something that someone has to give to us. This is just sample data. It's not every single Division I school. We then could use this count, right, function to count our total undergraduate variable. It's just going to count the cell if it has any value in it, and so that should return to us our sample size, or n, right? I think if you download the file, this originally wasn't there, so n, right? That's our sample size. I also believe the original one, I did this for the other class and I accidentally saved it earlier, so I apologize. There was nothing here, so you could just right-click, insert, give us another column, just so we have a nice reminder that these alpha values, an alpha of 0.1 corresponds to the 90% level, alpha of 0.05, 95, and then an alpha of 0.01, 99% confidence level, right? So we have the equations for the confidence interval. We can plug everything in. But the one thing that we can do in Excel, instead of doing it by hand to be a little bit more accurate, is to use Excel to find these z-values. So we looked at this function already. It was norm.s.i and b. So it said use the standard normal distribution and give me the z-score such that it would give me alpha in the tail. But we actually, on each tail, want what? Not alpha, but alpha divided by 2, right? We're looking at, well, I don't have it behind me anymore, but I'm going to write it down again. I'll actually write the whole thing out here. So we wanted to look up that z-score for alpha divided by 2. So the problem was, right, that would give me a negative value, and we said we don't want that. So I can then use that a function in Excel called ABS, which takes the absolute value of whatever's in its parentheses. So it's essentially going to take that z-value and just drop the negative sign, which is exactly what we wanted to do. Right? So I'm going to hit enter there. I then can copy this down, and notice it just updates the cell reference to be the next alpha value. So I've now found these 3 z-values. Notice when we used the table, we weren't exact. I think if you looked up, we had examples that used all 3 of these today. The 90% level is an alpha. We would look it up in the table. We had to choose the higher. We chose 1.65. It's actually technically 1.64485. Even that value that looked like in the table we could find, which was an alpha of 0.05, corresponds to that z-value of 1.96. But notice it's just a little bit below 1.96 to be perfectly accurate. And then 99% level, instead of 2.58, 2.5758, right? A little bit more exact than we were if we did this by hand, because we're not constrained to 2 decimals. So once I have the z-values, it's really just a matter of getting that confidence interval equation entered in, right? So I'll build my lower bound. I'll take my sample mean. I'll then subtract my z-value times the square root of my population variance divided by my sample size, right? I'm just using Excel to be my calculator here, right? I mean, that's exactly this equation. I'm just putting a cell reference in there for every single item, right? Because I have every single item somewhere in Excel, okay? Oops, there we go. Now, when I copy this down for different alpha values, right? I don't want to keep, I want my z-value to update, right? To correspond to the z-value for the next confidence level I want. But I don't want any of these values to change. So I'm going to put cell, around these cell references, $signs so that I freeze the cell references for the mean, the population variance, and the sample size, because those are always going to be the same. The only thing that changes when I go from the 90 to 95% level is my alpha and the corresponding z-score, right? So when I copy this down, L14 will keep updating. Okay, copy that down. Now notice what should be true. If I did something wrong here, where I saw the lower bound getting higher, that doesn't make any sense, right? Once I look at higher levels of confidence, we said that's widening. I have to include a wider range of values. And so for higher levels of confidence, my lower bound should be getting lower and my upper bound should be getting higher. Sure enough, my lower bound is getting lower here at higher levels of confidence. Any questions on that before we kind of keep moving here? Okay with that? Okay. Now for this next part, you could type this in for the upper bound again, right? Take the sample mean. Now you're adding that margin of error. So add the z-value, et cetera, et cetera. Or I think probably the best way to do that, highlight this, hit Control-C or copy it. Or you could right-click and copy or Command-C on a Mac. Hit Enter to get out of that cell. Go to this cell here, and then Control-V or Command-V and paste it. Right? Now the only thing I need, now when I copy and paste that way, when I don't drag it, Notice the cell reference didn't change, okay? I would then go change that sign, right? I'm adding that margin of error now to get my upper bound. Now I can just copy this down. It updates to the z value I want for that confidence level, but keeps using the mean, variance, and sample size, okay? Any questions on that? I mean, that's probably the easiest way to kind of copy and paste it over without retyping it in a bunch of different times. The nice kind of thing about this is if I wanted to do different confidence levels now, I could really just keep going down and figure out different levels of alpha, even if they were some strange ones. But these are kind of our 3 benchmarks that we'll see pop up a lot, okay? So we're okay with this? You want to see anything again, or? All right, so I think we're gonna have a little extra time. If you try to use this confidence.norm function, right? I would suggest not doing it. There's 2 reasons. I think that seeing the intermediate steps and setting it up something like this helps you get a better understanding of some of the functions that we're going to be using in Excel, like norm.s.inv. It also just kind of helps reiterate that equation for the lower and upper bound. You can use this confidence.norm to find. So what this is going to do is it's going to return to you like your margin of error, and you can add and subtract that to the sample mean. I would just suggest setting it up this way. I've seen people try to use it. I don't teach it for a reason, because it's very hard to use it correctly, right? And the name of it doesn't really correspond well to what it's actually telling you. And if you're going into the next, into the Excel assignment, try to mimic what I'm doing here, right? That's going to be the best way to do it, okay? Not just, I shouldn't say the best way in terms of like efficiency, but it's going to be, I think, the best for your learning, okay? All right. I had this other file that I thought was kind of interesting, a little thought experiment that I put up on Canvas as well. And it kind of just gives us more of an idea of what's going on with the confidence intervals, okay? So I had all this data, right, these grades that I submitted to the registrar for 431 students who have taken my business stats course, right? Obviously, their names aren't attached to them. They're in no specific order. It's just some actual population data that I have. This is every student who's gotten a grade from me. Right? So I found the sample mean of this, and I should say, I think I did drop like withdrawals and some things out of here. So this is why, it's a pretty good average. It's probably a little bit lower if I included people who withdrawal or just kind of like were enrolled and never submitted anything, right, and had zeros. But I can find my population mean by simply taking the average, right? So here's a weird example where I see the population data. I can actually find the population mean. I can find the population variance, right? I'm all good, okay? Well, let's say I then want to take a random sample of 50 people, right? I'll then calculate that sample mean. I then take another random sample of 50 people's scores, and I calculate that sample mean. From each one of these sample means, I then construct what a confidence interval would be based around that sample mean. So for the lower bound, this is the exact same equation that I had in the other slide. Excuse me. I'm taking my sample, well, you can't quite see it, my sample mean F54 right here. Now I skipped a step here. I didn't calculate the z-score in like a different row or column. I actually just plugged that function in. All right? So once I had that represents my z-score times the square root of my population variance over my sample size, which my samples were size 50. Okay? Now, I want to show you here. I'll go back to the other file for just a second. So if instead of finding this z-value first and referencing it with this cell reference, I could have just taken this and instead of using a cell reference now, I'm just going to put it all into one line. And I get the exact same value, right? So I'm just substituting there, cutting out kind of an intermediate step. Now you'll notice something here. I was showing you how to use the absolute value here. there's actually another way we could do this. So I had this drawn out earlier, I believe. But remember when I said if we want, so here's my z, here's my negative z, here's alpha over 2. Instead of looking at the absolute value, I could actually use 1 minus alpha over 2 just to get this positive z value, right? So that's all I did in that second file, was instead of using the absolute value, I just used 1 minus alpha over 2 here. Okay? Now I think in the original file that I had posted, I didn't have this alpha value up here. When I referenced it, I think I just typed in like 0.05 or something. But here, I'm going to actually use a cell reference up there for alpha. Okay? So this is really just my lower bound equation. Here's my upper bound equation, the exact same thing, but I'm adding that margin of error. So I've now got 1,000 different confidence intervals, right? So I look at the first confidence interval. It goes from 75 to 82. Does that include my true mean? True population mean? Sure enough, it does. So I put a 1 there. Now, how did I do that? I used some if statements. I'm not going to expect you guys to know how to do this, or even expect you guys to set something this kind of elaborate up. But if you're ever interested in like using if statements and stuff for other projects, other classes you have, I'm more than willing to talk about it because you can do some pretty cool stuff here in Excel with this. I then look at the next sample, 78 to 85. That includes the true population mean as well. I then keep going through. Well, notice for this sample, the lower and upper bound were 80 and 87. Does not include that true population mean. Okay? So for that one, I put a 0. I then just added up the number of times the confidence interval for each one of these samples included the true population mean. Notice, because so I didn't explain this cell to you, I'm not going to expect you. I was using this just to choose random numbers, and then I was using this to generate random numbers and look up various scores so that I was getting 1,000 different random samples of 50. Don't worry too much about that. Really what we want to focus on here is, did my confidence interval include that true population mean? And every time I hit enter here, it's generating new random numbers every time. So you can see at the 90% level, almost exactly 90%, right? Almost 900 out of the 1,000 samples have a confidence interval that includes a true population mean. And even if I keep generating new random numbers, yeah, it's a little bit above there, a little bit above there, a little bit closer, right? It just kind of, it's always right around 900. And the reason is why is because for me to get exactly 90%, I need an infinite number of samples. I've only got 1,000 here, but it's still pretty close, right? I can change alpha. Let's say I want the 99%, so 0.01 is my alpha. Now notice I'm getting right around 99%. This one's exactly 99% of my confidence intervals to include that true population mean as well. So this was kind of a unique thing where I had the population data. I then took 1,000 different samples from it, and sure enough, each 95% of those confidence intervals will include the true population mean. Okay. Like I said, I won't expect you to kind of set something up as elaborate as this, but it really is a nice way to kind of prove to us without having to walk through the mathematical proofs. Like I said, I always like to prove things to myself using data. For just I can see that this is holding true to those theories that we have. Also, just to show you kind of the powers of some stuff that we don't use in this class that you can use in Excel, right? So like, if I look at this cell, this VLOOKUP, like this is a great thing to know how to do. You can cross-reference against sheets and like look up different ID numbers and grab that person's like, wherever I wanted. Maybe I have age or height and like, so this is a pretty powerful tool. I'll sing Excel's praises forever. And if you guys ever have questions over it, I'm always, always more than willing to kind of help with stuff. So, but for the Excel assignment, I would kind of focus on this confidence intervals example file, specifically kind of when we have this known population variance or known population standard deviation. And then next class, we'll kind of start looking at how we do proportions in Excel. Okay, so how do we do population proportions in Excel? All right. I'm trying to remember where we stopped last class. I might just let you guys out a little bit early today. I think we worked through things a little bit quicker here, but I'm pretty sure we ended on Excel. Next class, what we'll do is kind of go through some examples of the population proportion, see that we can build confidence intervals for that as well, do a little bit of work in Excel, and maybe just begin talking about another type of distribution we have, which is the student T distribution. So I can't remember if I already did. If I didn't, I'll be putting the student T tables up there on Canvas. We might take a look at them on Friday. If not, for sure next week we'll be looking at that distribution, okay? Also, I don't know if it was updating on Canvas quite correct, but just as a reminder, I did extend that Connect due date to be the end of the day on Friday. I think it's showing up now, but I was having it is, okay. I was having some issues originally where it wasn't updated on Canvas, but it was updated on Connect, so it is open till the end of the day Friday, okay? Any other questions for me? Otherwise, I'll let you guys get out of here and I will see you on Friday. No questions? All right. I'll also get an online quiz up there today. It'll be due before class on Friday as well. Just like one question though. Oh, I got a question here.
Oh, yeah.
I'm assuming.
Because you were asking that one question with check the boxes, and then they all turned into questions that check.
Oh, okay. Yeah. No. It's basically if you submitted that, you're going to get the full points. I haven't been able to get on there and look at them yet. It was just the way I wanted the data recorded. So for last week's quiz, I'll get everything updated to kind of be accurate. Okay. Yeah. Sorry about that. All right. That should answer the question. So yeah, I'll get those updated actually once I get back to my office this afternoon. Okay. All right. That's it. All right. We'll see you guys on Friday.